I was supposed to be here now. Yes. First of all, I would like to take the opportunity. Right here, so. I would like to take the opportunity to thank the organizing committee and the foundation to give us an opportunity to come together. Is in such an outstanding environment. I've been working in fusion for long, and I've never been many conferences in other forums, but this is really worth mentioning. Thank you. So where are we now, and what are the challenges, technical, technology challenges that remain? I'm not going to talk about plasma physics. There are challenges in plasma physics still to be overcome. So I think first point, and thank you for Carlos to making an introductory speech which facilitated my life. Try to figure out a ladder. Commercialization and fusion is at the end of the ladder. We are moving up to this ladder, and we are at the beginning. So ITER, the precursor of ITER, JET, TFTR devices for the magnetic confinement, and NIF for the inertial confinement, have really demonstrated that fusion works, DT, okay? Now, we are realizing a project which is called ITER, which is producing fusion power. There are additional projects being constructed which have the same goal. Now, what we are going to cover in my talk is what are the key differences that characterize the next step, either in fusion confinement magnetic or inertial. And do not think that the next step is commercialization. We scientists has always considered an intermediate step. After ITER, there's going to be an intermediate step. Why an intermediate? Because yes, we will produce electricity, but not in a competitive way. For me, commercialization is to produce electricity in a commercially competitive way. So it's the second step. So the next step is what is indicated there. So we have to demonstrate, yes, fusion power, but in a plant, in a physical plant that doesn't break. So the availability of this plant is a fundamental element. So the reliability of the components that compose this plant has to be demonstrated and qualified. Because in contrast to ITER, in the next successor, reliability is an important point. Tritium has to be produced. Fusion burns 55 kilograms of tritium every 1,000 megawatt for 1 full power year. So every time you plan a fusion device with 1 giga of fusion power, and you want to operate this for 1 full power year, you need to have 55 kilograms of tritium. At the moment, resources of tritium are limited to 30, 40 kilograms, so, and they are decaying. So we need to have tritium produced by the next step. So self-sufficiency, production of the fusion is an important goal, and we need to see how we do it. We need to have materials which are withstanding the harsh condition of the neutrons, radiation-hardened material, which we are developing, qualifying. We have facility being fabricated with the purpose to qualify this material, to guarantee that the structural integrity of this material is defended. We need to be able to extract the energy which is deposited, in the case of magnetic fusion, DT, by neutrons. So you need to be able to use coolants at high temperature. And when you design a system at high pressure, then you enter a new domain of engineering challenges. But we have to do it if we want to get out the electricity. Now, just for those of you who are young, I'm a dinosaur, and I'm not optimistic, but I'm realistic. This is what has been done in the fusion domain in the world over the last 50 years. So on the top, magnetic confinement fusion. On the left, the US. On the right, the rest of the world. On the bottom, inertial confinement fusion. On the left, the US. On the right, rest of the world. The x-axis from 1970 up to 2015. Each one of these bars and the color characterize the custom, the type of... These are studies done in the US, in Europe, for magnetic confinement, and inertial confinement. A lot of fusion studies have been done. Very interesting work. But in a lot of cases, in all of them, a lot of assumptions that were taken proved to be very favorable, benign. We learn that to manage the power deposited by the plasma into very localized region, we call this problem power exhaust problem, is a hell of a difficult job. And it was forgotten in this part. A lot of technology which were considered for making this plant proved to be not ready. And there was a complete lack of thorough nuclear design, integration, and safety configuration. Result, everything went into the bin. Meters of documentation is in the bin. Now, new work is highly welcome, but we should not forget what has been done in the past. New technology, faster computer helps a lot, but I don't think it's enough. Don't forget that fusion is a nuclear technology, and as such, as it was clearly said by Carlos, it has to be scrutinized by a nuclear regulator. To move on the ladder, ITER mission remains fundamentally. It's a project which is complicated, not only because it's technically complex, but the only way to make it work is that we have to rely on international collaboration, which was historically composed of 4 members, been expanded to 7, is working ongoing. There's a lot of political interference from the very beginning of the design of this project, but it's a project which is going to make the difference. This project, in order to arrive to this project, which was described by Carlos, which is involving financially Europe very much, in particular, because the agreement was as Europe take on board around 50% of the construction cost, and the rest of the other countries take 9%. Now, designing and constructing ITER necessitated extensive R&D program, which were characterized by wide-ranging long-term international collaboration and major innovation. Lessons to be learned: the time for introducing and qualifying new materials, new technology and manufacturing processes has been a decades-long effort without assurance of success, because unfortunately, the devil is in the details. We made some progress. You see, we went from red to green. So it's good. The investment seems to be, but we're not there yet, because somebody mentioned we are at the level of readiness, which is good for ITER, but is not good for the next machine. We have to bring the technology from what is acknowledged to be level of 4 up to 9. And now comes the eightfold 8. I don't know if any of you have seen the movie of Tarantino. It was actually called The Eightful Eight. Now I'm going to produce for you a 5-course menu to describe what is, in my view, and I think is the view of the community, scientific community, what are the big challenges to overcome. So now, 1, tritium breeding. In order to run, we need to produce the fuel. And to produce the fuel, you need to have a component which is called the breeding blanket, which has never been built, has never been tested. If you don't do that, it doesn't work. Second, power exhaust, the management of the heat. We have investment in place. ITER will prove that this is actually working for tokamaks. We have existing configuration, other configuration, stellarator. It seems to be not more complicated. But for that, I think we are going to be able to get something established with the existing facilities. Remote maintenance. If you take, well, be distracted, look at the video there. We have to get the ship out of the cage, out of the bottle, put it there and take it out. So if you look at the investment we are making now in some of the facility we are developing, it shows the complication of the procedure. Remote maintenance. Developing neutron radiation hardened materials remain a question, because the property of this material under neutron exposure are substantially changing. And we have to ensure that these changes are properly encoded in the engineering design process. Otherwise, the system breaks. And if the system breaks, you have to take it out, time to replace it. You have to bring a new one, availability is down, cost is high. The heat extraction and the advance. So I would like to mention briefly, so what I mean a blanket is something which is not trivial. It's shown here in the middle. You have the plasma. Is there a laser or something I can point? So here is the plasma. The red one, surrounding the plasma, there is the first wall, okay? From the first wall out, there's going to be 1 meter of solid work, which is composed of a structural material, a multiplier, and a breeder, the one that allows this DT neutrons. The neutrons go through the wall. He starts making love with the lithium. It breeds. It produces other neutrons and tritium. So you need to have some sort of lithium-based components. And it's indicated in there. You have to cool it properly for 2 reasons. Because the temperature has to be controlled. Otherwise, this process, the tritium doesn't come out. And also, you have to cool it if you want to not to break the components, and you have to cool it to extract the heat. This 1 meter, we don't know how to do it. There are a lot of options. Liquid metal, solid breeder, beryllium, helium. What? So, a lot of good ideas. We never prove any of this. And in order to prove it and to qualify in Europe, we have a lot of installation, technology facility, where we are able to test small mock-up up to a level of 4. It's going beyond that we need to think on how to do it. So, I think we are converging internationally to recognize this to be the key. You see the curve, the tritium, we are now in 2020, will decay, because tritium decay naturally, and there will be a significant consumption of this tritium coming from ether. So if we don't hurry up, the tritium window for opportunity to start up a new device is going to close. Because in order to start a new device, you need to have a startup of inventory available. And the maintenance is an example of something which we have not yet developed to the level that we can demonstrate. We can lift and position this component in a realistic way. So we have, from my point of view, the key takeaways. A clash of conflicting needs. Yes, we have to accelerate. Yes, private investment is very important. I think it's fresh air. But we have to ensure that we have to together to join the forces to overcome the technical hurdle. So ITER has shown that time is needed. So proclaiming that fusion is going to be available in 2035, it means that you have to demonstrate that you are able to solve this problem within a given time, which we didn't do properly in the past. I think there is, and I welcome this technology proselytism. Everybody wants to help. Everybody wants to work, bring fusion. But please, do not just develop high-temperature superconductive magnets, because we know how to make the magnets. Of course, going to HCS, you do an improvement. But what we need to bring up are those technologies where the knowledge is very limited. And this is not the magnet. So I think it's important to realize that by developing technology in isolation without having a design or a project that drive the R&D priority, you're going to be fooling yourself. You need to have a project. Because it's only when you have a project that you know you develop a technology readiness, but together with an integration aspect. So because you risk here to developing a technology in isolation, and at the end you take it out, you have a technology 9, and then you cannot be integrated. So this is not a rocket. This is a very interdependent system. It's a system of systems. So I think you need to take that into account. So to me, we have to be able to distinguish from what I consider example of technology-driven innovation, which is important. Examples are the high-temperature superconductor. Examples are advanced cladding for the tungsten plasma-facing component, or more powerful 2 megagigatron for what is instead are examples of driven innovation. I put the picture there because I think here we have to be careful not to do the mistake, which is always good. People were looking at the ring under the lamp. I think we have looked under the lamp, and we didn't find the ring because we missed the ring somewhere else. So please, we need to go where the truth is, not where the process of seeking is easy. And I repeat, what are the other things? So we need a credible and attractive plan to deliver fusion, not just a promise. I think we are converging in what is needed. The problem is to find a way to converge in investments, in developing infrastructures that might actually help to bring this technology readiness up. Thank you. I hope